Hi everyone, today we are going to start our discussion about the electromagnetic waves. So from the chapter 19 to chapter 23, we have studied about the different properties of the electric and magnetic fields. So intrinsically, electromagnetic waves is nothing but just a combination of the electric field and the magnetic fields. Also, in the chapter 14, we study about the properties of the wave. So electromagnetic waves is nothing but just one of the example of the wave. So today we are going to study about how the electromagnetic waves is produced and propagate in the space. And we are going to study about the broad spectrums of the electromagnetic waves. So in the following lectures, I am going to simply say the electromagnetic waves in terms of the EM waves. So Maxwell is the first person to predict that our daily electromagnetic EM wave observed is actually the electric field and magnetic field propagating together and at a constant speed, and the speed is the famous speed of light. So what does it mean? It means that no matter what kind of frequency of the EM waves is produced, they all propagate at the same velocity. And this is a very unique property for the EM waves compared with other waves. So let's first study how the EM waves is produced. So let's look at the case A. So here it is an antenna and it is attached to the AC current. So what is the AC current? It means that the current comes out from this source. They change the directions. And in the lab, we use the so-called DC current. DC current means that the current always flows into the same directions. So this is very important. Please keep in mind in our following discussion. So now the antenna attached to the AC current. And now at the t equal to 0, the current is going in these directions. And therefore, positive charge will accumulate on the upper half of the antenna, and negative charge accumulate in the lower half of antenna. And we learned this one from the chapter 19, is that if you have this kind of charge contributions, the electric field is downward from the positive to the negative. And later on, because of the oscillation of the current, the charge accumulate on upper half become fewer and also in the lower half. So now the electric field is still downward, but it becomes smaller. So you will see that when the time is at 1/4 of the period, there is no charge accumulate anymore. And this is because the current is oscillation. So therefore, at this moment, there is no electric field. And later on, the oscillation of current flips. They change the directions. So now it is the negative charge accumulate on the upper half and the positive charge in the lower half. So there will be a new electric field produced, but now it is upward. And apparently, with more and more charge accumulating, the electric field will become stronger. So you will see that at a time equal to half of the period, this is just half of the wavelength. So from this diagram, you can see that simply, if the charge oscillate, you will produce a oscillating electric field. And this oscillating electric field will produce a EM wave. So also, a magnetic field also will be generated in this case. And the directions of the electric field and B field is perpendicular to each other, and both of them are perpendicular to the direction of propagation. So we will study this one later on with more details. But now let's try to study a bit more details about how the EM wave is produced. So this is basically the case. So you have an antenna here, and by change the charge accumulate across the two ends of the antenna, you could produce a voltage difference. And this voltage difference intrinsically means the difference of the electric field. So when the charge is oscillation here along the antenna, they will produce a difference of the voltage. And therefore, electromagnetic wave will be propagated outward through the charge accumulated here. So this is what happens. So let's take a look about this one. So this is basically the scenario A in the previous slides. So this is a direction of a current, and you will find out that you will produce a E field downward. And when the charge starts to oscillate, you will produce a EM waves propagate to the right. So the direction of the wave propagation is perpendicular to the electric field, the direction of the electric field. But the direction of the B field should simultaneously perpendicular to the electric field and the directions of the wave propagation. So therefore, the direction of the B fields is into the board. So you may ask why the B field is into the board, not out the board. I will answer these questions quickly in the few slides, within the few slides. But here I want to emphasize is that based on the property I just mentioned, if this is the direction of the wave propagation, and the B field and E field are all perpendicular to that, what does it mean? It means that the EM waves are the so-called transverse wave. So all the properties we studied before about the transverse wave can be applied here. So this is an example for the transverse wave. Yeah? So you can see the oscillation of the particles is perpendicular to the direction of wave propagation. So now let's continue. So how do you determine the directions? So let's try to see these pictures. So if the wave, EM wave, is propagating in the X directions, and the electric field is oscillating along the Y directions, then we can determine the directions of the B field should be in the Z directions. But should that be in the positive Z or negative Z? It depends on the relative directions. So here we need to study about the so-called right-hand rules. So the right-hand rule is that please point your fingers of your right hand in the direction of the electric fields, then curl it toward to the direction of the B field. Then your thumb will be the direction of the wave propagation. So let's take a look at this one. If your electric field now is in the positive Z directions, and you follow this direction and curl your finger to the direction of the B field, and you'll find out the right-hand rule tells you this is the direction of the propagations. So which means as long as you are given the information of the directions of two of them, you can determine the direction of the third component. So this is the direction of the wave propagation, direction of E field and B field. So if you are given 2 of 3, then you can determine the third one. So this is how the wave is propagated. But did you see that the current, AC current, what does that mean? It simply means that the electric charge is moving and accelerating within the antenna. So the most fundamental physics behind everything here is that as long as there's one electric charge, no matter how big the charge it carries, no matter it is a positive or negative charge, as long as the electric charge accelerating, they always radiate out a wave. This is the concept of the radiation. So the radiation is also a concept of the EM waves. So remember that the movement of the charged particles will produce the EM waves. So now let's have our first conceptual quiz today. So here I want to provide you a hint. So here you'll provide 2 different kinds of loops. One is made of plastic, one is made of copper. And they are asking about the induced current. So I just want to let you know that when the EM wave propagates through the loops, because the magnetic field is also oscillating during the propagation of the wave, so the magnetic flux passing through the loop also varies. So this is the point how you find out or determine your answers. So now let's take a look about the answer. So the answer should be B, and the reason is because based on the Faraday's law, if your B field oscillates, you will produce an induced EMF. So the delta V is your induced EMF. But here they're asking about the induced current. So the induced current is determined by the induced EMF divided by the resistance. And we know that copper is a conductor, so resistance is small. The plastic is an insulator, so the resistance is comparatively high. So therefore, that's the reason the induced current will be greater for the copper, even though the induced EMF is the same for both of them. And now let's talk about how fast the EM wave propagates in the space. So the speed of light, c, actually can be expressed in terms of the format like this. So I'm not sure, do you still remember the first one, the epsilon naught? It is the so-called permittivity in the free space for the electric field. And you see this constant in the Coulomb's law. And the mu naught is the permeability in the free space for the magnetic field. So you can see that for when we study the formula for the magnetic field. So you'll find out the speed of light, which is the speed of EM waves, is determined by the parameter from the electric field and magnetic field together simultaneously, not individually separate. So this one also tells you about that the EM waves is made of the electric field and magnetic field. And most important thing is that epsilon naught and mu naught are all constant. What does it mean? It means the C is a constant and it doesn't depend on anything. So it doesn't depend on the motion of the source or the observer. They all propagate in the vacuum at a constant speed. And this C value is 3 times 10 to the power 8 meter per second. And this is a very important fact and unique properties for the EM waves. So let me give you examples. So let's try to calculate that how long does it take for the light to propagate from the sun to the earth. So you can see that if you provide the distance, and the light is actually the EM waves. So the time spent will be the total distance traveled divided by the velocity. And now, because the velocity is a constant, so you make your life very easy. So it only takes about 500 seconds for the light to reach to the earth from the sun. And if you provide the distance from the earth and the moon, you will find out it takes only 1.3 seconds. So that's the reason that a lot of people will try to use the moon as a way to detect the effect of the gravity. So they will set a signal to a target on the moon and be reflected, and they can measure the time. So this is the time spent.